Example 2.1.2. A cosine wave representing a voltage source completes 3 full cycles in 1/20th of a second. Find both the angular frequency and the ordinary frequency of the waveform. Draw the voltage waveform for 3 full cycles if the amplitude is 10 volts. Label the horizontal axis in units of time, degrees, and radians. The givens for example 2.1.2 are that the amplitude of the voltage waveform, which we also call the peak value, is equal to 10 volts. We know that there are 3 complete cycles made. That's just the number of cycles, and then the time that it takes for the 3 cycles to complete is 1/20th of a second, equals 0.05 seconds. We are asked to find the angular frequency, omega, the ordinary frequency, which is given the symbol F, and a sketch. The solution is that I'm going to start just by drawing the 3 full cycles of the AC waveform. So I need an x-axis, which is going to represent, sorry, a y-axis, which is going to represent my voltage. And then, oh, that's terrible. And then a x-axis, which represents my angle or time. That can be in units of seconds, or it can be in units of radians or units of degrees. So seconds is related to time, and then radians and degrees are just 2 different ways to measure that angle. So gonna get some units here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 13 different equally spaced units. You can approximate that. We know that the cosine of 0 is 1, which means cosine has a maximum value at angle equals 0, so that's going to be the 10 volt max. Then at 90 degrees or pi over 2, it's going to go down to 0. And then at 180 or pi, it's going to go to its negative value, negative 10 volts, about right there. Then at 270 or 3 pi over 2, it's going to go back to 0. And then at 360 degrees or 2 pi, it's going to go back to its peak value. So that's one complete cycle right there. So I can just repeat that 2 more times, and I'll get 3 full cycles. So I'm just drawing dots to show where the different significant points are. And this isn't a perfect AC representation of the cosine, you know, but it's pretty good. So that's what the cosine waveform is going to look like. We call the peak-to-peak time it takes there T. That's one period. Another way to say that is 1 cycle. So since this takes 3 cycles to do, or we know that 3 cycles here from here to here took 1/20th of a second from the problem statement. So that's 0.05 seconds, or 1/20th of a second. We can go ahead and easily calculate that one of these cycles is just a third of that, or a 60th of a second. So we can calculate the ordinary frequency of that. We just know F is going to be equal to 3 cycles over 1 over 20. Or we could say that there's 1 cycle over 1 over 60, just by looking at that waveform. Either way, we're going to get F is equal to 60 hertz, 60 cycles per second here. So that gives us our frequency. The angular frequency is just converting that from cycles per second, or hertz, to radians per second. So we need to convert from cycles to radians. In 1 cycle, there's 2 pi radians. So that gives us the formula omega is just equal to 2 pi f. So if you've ever wondered why we do that, multiplying by 2 pi, simply it's 2 pi radians per cycle, and that's 60 cycles per second. And so that's just a conversion there. So we get 2 pi times 60, and that gives me 120 pi rads per second. Sometimes people write that as 377 rads per second, so that is the AC frequency in radians per second of the North American electric grid. So that gives us our frequency information and our angular frequency information. The last thing we were asked to do was annotate this graph with time and angle. So we started doing that a little bit. We know that this is 0 degrees or 0 radians. We know that this here is 90 degrees or pi over 2 radians. We know that this is 180 degrees, or the next would be 2 pi over 2, which simplifies to pi radians. This is going to be 270 degrees, which is going to be 3 pi over 2 radians. And then this is going to be 360 degrees, which is just going to be 4 pi over 2, or 2 pi radians. And that would continue on and on and on. And so that satisfies that requirement right there. The next question is, well, we're also asked to specify what these units are in terms of seconds. And so we'll use the angular frequency to determine the time here. And so if we took, just do a little side math here, if we did 0 radians and we multiply it by 120 radians per second, we can, not multiply, we divide it. And so we get 0 seconds there. So that 0 radians is at a frequency of 120 radians per second is also 0 seconds. If we were then to take pi over 2 rads and divide it by 120, I left the pi out there, 120 pi rads per second, we would get 0.004167 seconds. So that's that right there, 0.004167 is when it goes to 0. And we know that unit's constant, so we could keep doing math like this, or we could just increase in increments of 0.004167. And so that value right, if we do that, that value right there is going to be 0.00833. That value right there is going to be 0.01. Nope, I skipped one. Sorry, that value right there is going to be 0.0125. And then that value right there is going to be equal to 0.01667 seconds. And since this was a 60 hertz waveform, we now know that the voltage waveform in the US power system, it repeats itself every 16.7 milliseconds. That's the time period there, 16.67 milliseconds from there to there. Which is also just 1 over 60 hertz, by the way.